If you've been 3D printing for any length of time, you already use a slicer constantly. Cura, Prusa Slicer, Orca Slicer, Bamboo Studio, pick your poison. You load a model, tweak some settings, hit slice, and out comes a preview full of colored lines. Then you send it to your printer and hope it works. Most people treat the slicer like a magic box. You change numbers until the print looks better, but you don't really know why it worked. And when a print fails, the slicer is often blamed even though it's doing exactly what it was told to do. To really understand 3D printing, you have to understand what the slicer actually does. Not at the "it cuts the model into layers" level, but at the level of how it turns geometry into motion, pressure, heat, and timing. Because your slicer isn't just a file converter, it's a translator between digital geometry and physical behavior. Everything starts with the model. When you load an STL or 3MF file into your slicer, what you're giving it is not a solid object in the way humans think about solids. It's a collection of triangles that describe a surface. The slicer doesn't know what's inside the object. It only knows where the boundaries are. This is why things like non-manifold edges, flipped normals, and holes in meshes cause problems. From the slicer's perspective, those errors make it ambiguous where material should exist. Before anything else happens, the slicer has to interpret that surface and decide what volume is printable. Once the slicer has a usable model, the first major conceptual step happens, slicing the model into layers. This is not just cut it every 0.2 millimeters. The slicer is intersecting the model with a series of horizontal planes. Each intersection produces one or more closed 2D shapes for that layer. Those shapes represent where plastic should exist at that height. Already, decisions are being made that affect strength, surface quality, and time. A smaller layer height produces more slices, more transitions, and more opportunities for detail, but also more chances for error and more time spent accelerating and decelerating. Once the slicer has those 2D shapes, it has to decide how to fill them. This is where perimeters come in. Perimeters are the outlines of each layer. When you tell the slicer to use 2 or 3 walls, you're telling it how many offset contours to generate inward from the original shape. Each of those contours becomes a continuous extrusion path. This is critical to understand. Walls are not decorative. They are the primary structural component of most prints. In many cases, the walls carry more load than the infill. When you increase wall count, you are not just thickening the surface, you are changing how forces flow through the printed part. The slicer generates these perimeters first because they define the shape and seal the inside of the print. Everything else happens inside those boundaries. Now comes infill, which is one of the most misunderstood parts of slicing. Infill is not there to make the print solid. It's there to provide internal support, resist deformation, and give the top layers something to bridge across. The slicer takes the interior area of each layer and fills it with a pattern. That pattern is chosen based on your settings, grid, gyroid, cubic, lines, and so on. But what matters more than the pattern name is how the slicer uses it. Infill is usually printed faster, with less precision, and often with less cooling consideration than walls. The slicer treats infill as a structural filler, not a cosmetic feature. This is why increasing infill percentage often has diminishing returns. You're adding more plastic, but not necessarily in the directions that matter most for strength. Orientation and wall thickness usually dominate strength far more than infill percentage. Once walls and infill are planned, the slicer has to deal with one of the hardest problems in FDM printing: top and bottom surfaces. Bottom layers are printed directly on the bed. The slicer slows down, increases extrusion width, and often increases flow to help the plastic bond to the build surface. This is why first layer settings matter so much. The slicer is intentionally over-extruding slightly to compensate for microscopic gaps and surface imperfections. Top layers are different. They're printed over air or infill. The slicer has to ensure that each top layer is supported well enough by the layer below. This is why top layer count matters more than infill density for surface quality. If the slicer doesn't have enough solid layers, you get pillowing, sagging, or visible infill patterns bleeding through. At this point, the slicer has a complete geometric plan, but geometry alone doesn't move a printer. Now the slicer becomes a motion planner. Every line you see in the preview is a toolpath, a sequence of movements, each with a speed, acceleration, and extrusion rate. The slicer converts geometry into commands, usually G-code, that tell the printer exactly how to move. This is where physics enters the picture. The slicer has to account for how fast the printer can accelerate, how sharp corners affect pressure in the nozzle, and how long molten plastic takes to respond to changes. Even though you don't see it directly, the slicer is constantly making trade-offs between speed and quality. For example, when a toolpath approaches a corner, the slicer often slows the printer down, not because the printer can't physically make the turn, but because extrusion pressure needs time to stabilize. If the printer takes the corner too fast, plastic piles up and you get blobs or bulging. This is why features like jerk, acceleration control, and pressure advance exist. They're attempts to model and compensate for the lag between commanded extrusion and actual plastic flow. The slicer also has to manage retractions. Whenever the print head moves without printing, the slicer decides whether to retract filament. That decision is based on distance, speed, and context. Too few retractions and you get stringing. Too many and you grind filament, introduce delays, and increase wear. What's important here is that retraction is not a property of the printer alone. It's a choreography between slicer decisions and hardware behavior. Two slicers with identical retraction settings can behave differently because they plan travel moves differently. Cooling is another layer of complexity. The slicer controls the fan based on layer time, material, and geometry. Small layers cool too quickly. Large layers retain heat. Tall, thin parts behave differently than wide, flat ones. The slicer uses heuristics to decide when to slow down, when to increase cooling, and when to leave things alone. This is why prints sometimes fail even when all settings are correct. The slicer is making assumptions about heat transfer that may not match your environment, filament, or printer. Supports are where the slicer's limitations really show. When you enable supports, you're asking the slicer to generate temporary geometry that exists only to be removed later. The slicer analyzes overhang angles and identifies regions where plastic would otherwise be printed in mid-air. It then creates support structures designed to be strong enough to hold material but weak enough to remove. This is an inherently imperfect compromise. Supports are not structural in the same way the model is. They are scaffolding. The slicer chooses patterns, densities, interface layers, and gaps based on assumptions about material behavior. That's why support tuning is so finicky, and why no slicer produces perfect supports in every case. Now let's talk about something many people don't realize. The slicer is also a scheduler. It decides the order in which features are printed. Which wall first? Which part of the model next? Whether to print layer by layer across the entire plate or finish one object before moving to the next. This ordering matters. Printing small features first might cause them to overheat. Printing tall features early might lead to collisions or cooling issues later. Multi-object printing adds even more complexity. When you enable options like Print Outer Walls Last or Optimize Wall Printing Order, you're influencing how the slicer schedules work, not just how it draws lines. Even seams are a scheduling problem. Where the slicer chooses to start and stop extrusion on each layer determines where seams appear. You can tell the slicer to hide seams on corners, align them, randomize them, or place them on the back. Each option is a different strategy for dealing with an unavoidable artifact. The seam exists because extrusion has to start and stop somewhere. The slicer's job is to make that transition as invisible as possible, but it can't eliminate it entirely. At the very end of slicing, everything is compiled into G-code. G-code is not smart. It doesn't know about models, layers, or infill. It's a low-level instruction stream. Move here, extrude this much, set temperature, turn fan on, wait. All the intelligence lives in the slicer. This is why two slicers can produce very different results from the same printer and the same model. They have different assumptions, heuristics, and priorities. Some favor speed, some favor surface quality, some are tuned for specific hardware ecosystems. When a print fails, it's tempting to say, the slicer messed up, but in reality, the slicer did exactly what you told it to do. The failure usually comes from a mismatch between assumptions and reality. Understanding the slicer means understanding those assumptions. The slicer assumes a certain nozzle diameter, a certain filament diameter, a certain flow consistency, a certain cooling capacity, a certain mechanical response. When any of those are off, the plan no longer matches the physical world. This is why blindly copying slicer profiles from the internet often leads to frustration. Those profiles encode assumptions about machines, materials, and environments that may not match yours. Mastery in 3D printing doesn't come from memorizing slicer settings. It comes from understanding what the slicer is trying to achieve and helping it succeed. Once you understand that the slicer is a geometry processor, a motion planner, a thermal manager, and a scheduler all at once, its behavior stops feeling random. When you change a setting, you're no longer trying something. You're adjusting a lever that affects a specific part of the process. And when something goes wrong, you can reason backward. Is this a geometry issue, a flow issue, a cooling issue, a scheduling issue? That's the difference between tweaking and understanding. Your slicer is not magic. It's software trying to model a messy physical process. The better you understand its model, the better your prints will be. Let us know in the comments what your favorite slicer is. Please like and share this video if you found it helpful. Subscribe for more 3D printing content. And thanks for watching.